given a talk on theory of quantum gravity of 1D objects. Over to Dr. Kulshreshtha.
Okay. Thank you, Madan Lal ji. Thank you very much, and thank you, Dibya Madam, for your very, very kind words and for your very kind introduction. So, in fact, I am equally happy, just like all the young participants. I understand 82, so I am overwhelmed from all over the country. That's a great thing, and I am also grateful to you people, you personally, Madan Lal ji, Dibya ji, and Professor Sanjay Jain, and the entire physics department of the Kumaon University Nainital, and my very, very, very special thanks to the participants. You see, the most ingredient component for any such workshop, program, course, or conference, the most important ingredient is the audience, is the participants, and I'm very happy that the people are also full of enthusiasm. That is what I really need. You see, mind automatically starts working when you are sitting in front of the people who are curious minds, who are enthusiastic for learning something. And this puts also some responsibility on me that I would try to fulfill, namely that the participants expect to know some path-breaking things, some path-breaking ideas in the talks, and they give their valuable time for this. So with that, with all my thanks to all of you, to all the participants of all the institutions, I then come to the topic of my talk. So the topic of my present talk, this is my first talk. I am supposed to be giving two talks. So second talk is on superstring theory as the theory of quantum gravity of one-dimensional objects, which are strings. But in this present talk, the title, and I'm going to talk about supergravity theory, which is a candidate theory of quantum gravity, just like the superstring theory. These are two different alternative approaches towards the same goal, and I would illustrate, I would explain in my talk how do we go about it. And I would request all the participants and audience to please keep reminding me in between at various points how to handle it, how to go about it, how to understand it. Okay, and this is what I would try to do. Okay, so all right, as the talk suggests, some by the name supergravity. So before that, I mean, the first question that comes to mind, what is gravity and what is super about it? So let me start with the very simple ideas, namely the Big Bang, that you see our universe came into existence something like 13.7 billion years ago, and all the fundamental laws of nature were also born right at that time, and we try to understand them, analyze them, and make progress about it. So as of today, right now, we have two great fundamental theories of nature at our hand. One of them is the quantum theory, and the other one is the gravity theory, or the theory of general relativity. And I would tell you, convince you, that in fact the two are not very far from each other, you see. So quantum field theory, quantum theory, means quantum mechanics, quantum field theory, and so on. So, in fact, quantum field theory is also, quantum mechanics is also quantum field theory and vice versa. So, generalization of quantum mechanics is quantum field theory. And this conventional term called quantum field theory refers to a theory in flat space time, Minkowski space, conventionally 4 dimension, but you can consider any dimensions that you like. And general relativity or the gravity theory comes about when we talk about the quantum field theory in curved space-time manifolds. So when you talk about curvature or curved space-time, gravity automatically comes into the picture. You see, all of you must have heard the famous quote, which I would explain what it really means, that mass tells the space how to curve, and the space tells the mass how to move. This is in fact a simple interpretation of the Einstein's equation, which we encounter in general relativity. So, conventional field theory means field theory in flat space-time, Minkowskian space, and general relativity means field theory in curved space-time. So, when you consider curved space-time, gravity automatically comes in. Now, you see, for learning quantum theory or quantum field theory, both these theories, quantum field theories as well as general relativity, they are the not only most fundamental theories of nature, you see, they have been experimentally verified up to several digits. Therefore, they are the most accurate theories of nature in their own domains. So, quantum theory holds true for small distances. It describes the laws of the microcosmos, the universe inside the atom. And general relativity tells us about the cosmos, the solar system, galaxy, black holes, wormholes, time travel, and everything. So the scales are vastly different. Okay. Now we know of special theory of relativity. This tells us the equivalence of mass and energy. This is a special theory of relativity equal to mc square. Even it's written in several restaurants at many places, equal to mc square, along sometimes with a picture of Mr. Einstein. And quantum mechanics, quantum theory tells us that there is a possibility of the existence of a vacuum. Vacuum state actually is not empty, but it's a boiling soup of particles being created and destroyed continuously. So this is what is quantum theory, and when we write it down as a field theory, which means all the fields are just functions of x, y, z, and t. So for example, the simplest and best known field theory is electrodynamics, which was invented by none other than Mr. James Maxwell almost 150 years ago. And this is the best studied theory. So you see, most of us, we are doing in one way or the other electrodynamics, which is Maxwell's theory, and quantum theory, whether relativistic or non-relativistic does not matter. But most of us are doing that. And of course, classical theories are the mother theories of nature. You can construct corresponding quantum theories using conventional or suitable appropriate methods. And so both of them are equally important, and both of us, they are rich. And why I said classical theories are the mother theories, because you can always construct and derive the corresponding quantum theories out of those classical theories. You see, so this is now the conventional field theory describes quantization of three fundamental forces of nature: strong, weak, and electromagnetic interactions. And it can be summarized into the so-called standard model of particle physics. And this model uh, describes the quantization of these three fundamental forces of nature. And of course gravity is left out, or is not, simply not there, because we are, as I said, we are talking about the flat space. So when the space is flat, the gravity would automatically disappear from the theory. There would be no gravity in that theory. So it has its own successes, in fact, and it is based on the relativistically invariant quantum gauge field theory. And now, what are the contents of this theory, the standard model? It has been verified up to several digits at experiments like CERN and Fermilab and DEGI and many other experiments, KEK and so on. So it has been verified up to several digits. So what is the net result out of this? What are the contents of? What is the particle content of this theory? We have at our hand 6 quarks, 6 leptons, and the factor gauge bosons. So photon for the electromagnetic interactions, and gluons for the strong interactions, and W plus, W minus, and G0 for the electroweak theory. And you see, each one of them, it's not so important to count the number of Nobel Prizes that have gone into this. Each and every finding has won the Nobel Prizes, whether theoretical ideas or experimental finding. The things go hand in hand, you see. All the people work together as a team globally on the planet, and we are living in happier and lucky times that there is a lot of media available. You have several platforms like email, internet, and everything. People can get connected throughout the world, and they can keep working on the progress and development of these theories. So these 6 quarks, 6 leptons, and the vector gauge bosons, and of course the unique Higgs scalar, the God particle, as people call it. So that is the Higgs scalar, or the Higgs particle. This is the total particle content of the theory, and well studied, and is still in the progress from theory as well as from the. Now there are a few important points about this standard model or the conventional field theory. This is a theory which is a gauge theory. What is a gauge theory? In a gauge theory, the gauge symmetry is local gauge symmetry. Local gauge symmetry, where the transformation parameter is a function of x mu. Itself, transformation gauge parameter itself is a field, it's a function of x mu. So that is the thing. And this, if you consider any simplest gauge theory, not to talk of directly the standard model containing all the 3 fundamental interactions, if you consider the simplest field theory that we teach in the classroom, I have done it for decades now, my main field, the quantum field theory. So quantum electrodynamics, which describes the electron, positron, photon field. This is the simplest field theory that we can think of, and this is the theory which we always take as an example in the classroom. This is the, so electron, positron, photon field. If you consider what is the outcome of this theory, by calling that this has local gauge symmetry, you can prove that the local gauge symmetry here, you in your electrodynamics you say d mu j mu equal to 0. So j mu is the vector current density. You multiply it with dqx and integrate it over the, or sum over the entire space, and then for the spatial components you convert it into the volume integral, I mean, you multiply it with dqx, so this is a volume integral. You convert it into a surface integral, and this surface integral of divergence j over all the space, this would vanish over the infinite uh, spatial boundaries. So you are led to the result that d mu d0 j0 equal to 0. And if you integrate it over time, this little j0 becomes capital J0 or the charge q. So d by dt of q is 0. What it means? It means that total charge of the theory is conserved, and it is the outcome of the conservation of charge, which is itself is a consequence of the local gauge symmetry of the theory, of the QED theory, that we say, okay, electronic charge is conserved. What is the electronic charge? This is the conserved charge of the QED theory. For this reason, you measure the electronic charge in Delhi or in New York or in Germany or wherever you are sitting. It would be the same. It would be the same today, it would be the same 100 years or 1000 years later. Okay. So, that is the power of the conservation laws, and that is the power of the gauge symmetries of the theory. So, this is one thing we have talked about. Now, let me talk briefly. I will come back to it again, but before that, let me mention the gravity theory, general relativity. This is also extremely successful. And general relativity, the theory of gravity, which is described in terms of curved space-time, this is a very unique theory, you see, where the theory was verified experimentally 70 years earlier than it was born. The theory was born in 1915 at the hands of David Hilbert and Mr. Albert Einstein. And 70 years prior to that, there was a famous French astronomer, Leverrier. Leverrier accurately measured, he was an astronomer, he accurately measured the advance of perihelion of Mercury. What is the advance of perihelion of Mercury? If I consider the motion of Earth around our Sun, and after 365 days, it is supposed to come back at its original position, but the major axis of the ellipse in which it is rotating gets rotated slightly. This is called as the advance of perihelion of Earth. The same would hold true for the advance of perihelion of Mercury. Mercury is the tiniest, smallest planet of our solar system, and its orbit of motion around the Sun is also tiny. We take 365 days for one revolution, and Mercury takes about only 88 days. So, Leverrier was able to measure accurately the advance of perihelion of Mercury, which when turned to per century, it is about 43 arc seconds. And you see, this tallies exactly, perfectly well with the prediction of the of this advance of perihelion of Mercury based on the general theory of relativity. The two agree identically, perfectly. They perfectly agree with each other. This is so the theory was born 70 years prior to its birth, as I like to describe it. You see, now there are, of course, modern tests of the theory of general relativity, actually just spread during the last 10 years or so, less than a decade. All of you must have heard about LIGO experiment, the gravitational wave detection at LIGO experiments. You must, because these things, they made headlines in the newspapers also. And then the black hole image, construction of the image of a black hole. This black hole that was considered is sitting at the center of a galaxy called M87. This is a distant galaxy from our own Milky Way galaxy, and a supermassive black hole. I mean, it's 6 to 7 billion times heavier than our solar mass, the mass of our sun. and its spread is 40 billion times the size of our solar system. So you can imagine how massive, it's a super massive giant of black holes. Giant of black holes. And you see, based on our observations through eight, through an array of eight event horizon telescopes that are spread all over the earth, and through that the smart experimentalists, they have been able to construct the image of this black hole. It was in the newspapers all around. You just write and you find it. So, and then our in the year 2020, the Nobel Prize went to Mr. Penrose, Andrea Gage, this woman physicist. I am a great admirer of Andrea Gage, and Mr. Reinhard Genzel. These three guys this year. Mr. Penrose, I had the golden opportunity of talking to him twice while he was in Delhi, when he gave two talks here, and I had a personal conversation with him after his talk. I will come back to it later. So, Penrose predicted that a massive black hole exists even at the center of our own Milky Way galaxy. And the location of this black hole is referred to as the Sagittarius A star or SGR A star. Now, it's a supermassive black hole, so must be thousands or millions of objects may be revolving around it. One of them is SO2 or simply S2. So, this brave woman physicist, Andrea Gage, she picked up one particular unique object called SO2 or S2, which takes about 16 plus something, 16, little more than 16 years to make one revolution around this supermassive black hole sitting at Sagittarius A star. So, you see, this Andrea Gage, she measured it continuously for more than 16 years. And advance of perihelion, she worked out from this advance of perihelion. So, experimental finding of the advance of perihelion of this object, SO2, around the Sagittarius A star. And you see, this tallies exactly again perfectly well with the prediction of general relativity led by Mr. Roger Penrose. So this is the most modern, most recent test of general relativity. So we are now convinced that okay, these two theories are very accurate theories of nature, experimentally verified. Now, what can we do about it? We come back to our conventional field theory standard model. As I said, it has a gauge symmetry and it does not have gravity into the picture. It's in the flat space-time manifold. Now, so how do we go about it? How do we understand it? Now, before we understand that, there is a very important question. In the first place, there is one important question in general relativity and gravity theory itself. This is the question of singularities. Singularities, for example, if we run the universe backwards in time, we hit upon a singularity called as the Big Bang. This is the most giant, biggest singularity of nature. Black holes themselves are a kind of singularity, and if you go inside the black holes, the space-time gets curved to the Planckian scales. You see, when you go back to Big Bang by running the universe backwards in time, what happens? Slightly before you hit upon this singularity called Big Bang, the space-time gets extremely curved, and we reach the Planckian scales of energy, time, and distance. Distance is 10 to the power minus 33 centimeters, time is 10 to the power minus 43 to minus 44 seconds, and energies are of the order of 10 to the power 19 GeV. So we hit upon this scale, Planckian scales, and here general relativity breaks down. This is the point. So general relativity being so successful, so accurate, experimentally verified, it breaks down at certain points, mainly at the singularities. So when I refer to singularity, black hole as a singularity and singularities inside the black hole, I would like to give a very simple example to my younger participants, that we know that what is the uh, potential energy, gravitational potential energy. And before gravitational potential energy, what is the escape velocity, what is a black hole? We all know, we pick up a particle and throw it outside from the surface of the earth. If it reaches a certain value called the escape velocity, the guy never comes back to earth. That is what you call as the escape velocity. Okay, so which is square root of 2 mg by r square. So now what I would like to do, if I keep the mass of the earth fixed at the value what it is, and I reduce the radius of the earth continuously, keep reducing the radius of the earth but keeping mass fixed, then what happens, a stage will come when the earth, the radius of the earth would reach something like 8.43 millimeters. Earth would become a very spherical, tiny spherical ball. And the escape velocity, if you calculate from that formulae, at this time the escape velocity would be identically equal to the velocity of light. What does it mean? Even if I throw a photon from the surface of earth, with the velocity of light, photon travels with the velocity of light, it will never fall back on earth. That would be the situation that we call a black hole. So this is how we can understand, visualize what is a black hole. For our sun, it would be something like 3 kilometers, when the sun would become a black hole. This limit is actually called as the Schwarzschild radius of an object. For each object, it holds for each object. You can calculate for yourself or myself. So for Earth, it is 8.43 millimeters. Then the object becomes a black hole. So this is a singularity. Now, when I talk about singularities inside the black hole, let me consider the plot of gravitational potential energy, and I would like to give it as a homework to all of you. Please do it after your workshop or conference. Try to plot this. So this potential energy phi of x, let us say, minus g capital M by mod x. So this is the potential energy due to a mass m sitting at the origin. So potential energy at a point x is phi of x minus gm by mod x. I did it once traveling in the train. And so you can put g equal to 1, you can put m, first initially put m equal to 1 and take mod x equal to 1, then 2, then, so x equal to 1, mod x is plus minus x. So it's a symmetrical curve, okay? The phi x would be a symmetrical curve around the axis of y. Now, you take m equal to 1 to 10, 100. I'm sure you will not be able to plot when you go to m equal to 100. M equal to 100 m. Okay? So, this potential, if you like to call it a bell, it will become narrower and narrower and deeper and deeper and deeper. So just think, if you make this mass of the black hole to be 1000 of this m or 10,000 or 1 million of this m, what would happen? You would end up with a situation where it would be too narrow, and the space-time inside this, if you like, consider a softie, ice cream. Okay, but make it narrower, narrower, narrower. Plot it, please do try it. It's a simple plot. Phi of x equal to minus gm by mod x. Plot a few points to just have an idea what you get. It's so deeper, then that would give you precisely the idea of what could be a black hole. Okay, so and what happens when you go inside the event horizon, which is an imaginary surface outside the black hole, and beyond that you cannot go inside it, because as I told you, the your normal conventional general relativity things will would change. This will no longer work, as I have just illustrated that it becomes a singularity and so on. So this is one point. And how do we again handle it? This only tells us an idea that general relativity, after all, has limitations. It would break down at certain limits. Okay, it will no longer work. And but still we are interested in the domain where general relativity might not work. So then what would we like to think? Then we would like to think, could there be a theory of quantum gravity? If yes, how do we go about it? Now, before we go to a theory of quantum gravity, which I just said, it could be considered in two different alternative ways. But why two different alternative ways? Before that, I must tell you the question of divergences. Question of divergences in theory, in field theory. We all are familiar with the Coulomb law of force. The force is Q1 Q2 by R square. So when R goes to 0, the force blows up, and this is a singularity situation. Now, so because of this, there would be divergences. How do we remedy it? Fortunately, we have Heisenberg uncertainty principle to help us out. So delta x is as crossed by delta p. Now, in simplest field theory, QED theory, the interaction Hamiltonian is some iota times E0 times psi var a slash psi. Why have I called it E0? This is in fact the bare charge of the electron. So I like to introduce you the concept of a bare charge and bare mass of a particle. And for higher order diagrams, you consider product of these interaction Hamiltonian at 2 points, 3 points, n points, and so on. And you can develop the covariant perturbation theory, which you get as a generalization of the Dyson equation. Okay, which you get. You consider time evolution operator in quantum mechanics. You invert it, the differential equation, Schrodinger equation for time evolution operator. You invert it into an integral equation, make iteratively integrations, you end up with the Dyson series, which is an infinite series of multiple products of these integrations. And here in quantum mechanics, h is a function of time t alone. In mechanics, all q's and p's and h and everything, it's a function of time and time alone. In field theory, it is a function of x mu, which is x by z and t. This is the difference. So therefore, you need to generalize Dyson series in quantum mechanics to covariant perturbation theory. And now I said, so the interaction, you talk about I told you the contents of a standard model, 6 quarks, 6 leptons, gauge bosons, and so on. But how, it is not enough to know them. It is interesting is how do we talk to each other? Like I am talking to you, you are talking to me. So how do these particles talk to each other? This is what is understood well in terms of the so-called Feynman diagrams. This is the Feynman diagrams. And so like for the QED theory, I said psi var E slash psi, you split it, each three of them into positive and negative frequency parts, take the product, you get 8 terms. These 8 terms corresponding to 8 fundamental vertices of the QED theory. So like electron scattering with the emission of a photon, electron scattering with the absorption of a photon, positron scattering with the emission of a photon, positron scattering with the emission and absorption of photon, E plus E minus annihilation with the creation of a photon or with the absorption. This is how you get 8 fundamental vertices in all theories, QCD theory, electroweak theory. You first have to get the fundamental vertices, and with the help of fundamental vertices, you can construct higher order diagrams, which makes sense because the fundamental interaction in the first place has only one vertex, and if you calculate its transition amplitude, it will come out to be identically zero. So at least it has to be two. So only even orders of diagrams they contribute, and odd orders they all contribute to zero. This is what we teach in our theory. You can derive it in using the standard textbooks. Okay, fine. So now you will say, what is the problem? The problem is the here you see, let us think of a very simple trivial situation. You might laugh at it. We are taking bath in our bathroom, and unless we wrap a towel around us, we are a bare particle. We cannot talk to anybody. We are a non-interacting particle. We are not a physical particle. Once I wrap my clothes around, then I'm a physically interacting particle. I can talk. If somebody comes, I can say, hello, okay, there I am, and so on. So that is physical. Now, what is the difference in these two? This, I said, the towel or... So actually, that what happens in field theory, the force strength of a force or the coupling constant, it varies with distance or time. It varies with distance or energy. So, and in fact, these are called as vacuum fluctuations. So, the vacuum fluctuations can be calculated in field theory, and they turn out to be infinite. If that is so, then my bare property, charge and mass of the electron, they must also be involving infinities. They must also be infinities. And the two add up in a very sensible manner to give us finite results. Okay, this procedure is called as renormalization. And essentially, it makes use of your Heisenberg uncertainty principle. Based on that, conceptually, now, so in every theory, in QED theory, for example, there are three fundamental lowest order radiative corrections. For each theory, you can find what are the lowest order radiative corrections for that theory. So for QED theory, self-energy of a fermion or an electron. So electron is propagating, it emits a photon, it reabsorbs that photon. This is electron self-energy. A photon is traveling, it splits into a pair of electron-positron, and it again recombines into a pair of electron-positron. This is called photon self-energy and vertex correction. Okay, so these are three. And with the help of these three lowest order radiative corrections, we can develop sensible theories, and we can relate the properties of the bare particles with the properties of the physically interacting particles. So for example, a photon propagator which involves the bare charge and mass of the electron, I can calculate it in terms of the propagator of an electron, physical interacting electron. So it would involve only E and M plus the electron self-energy. The same thing holds true for the photon propagator in terms of the bare charge and masses given in terms of the the properties of the physically interacting particles plus a photon self-energy diagram. So this procedure is called as renormalization, and it consists in relating the properties of the bare particles with that of the physically interacting particles. So this is what is the towel going to do for us. You see, when the electron is scattering with the emission of photon, it's a non-physical process. For physical process, you have to be able to measure something. Okay, so with that, now it is clear that we have to have some approach to handle this, and this is the conventional field theory which describes a standard model physics. Here things are manageable in terms of the renormalization theory. Okay, now If I want to consider gravity into my theory, then what do I need to do? In the first place, my Heisenberg uncertainty principle would no longer work, because in my uncertainty principle, delta x is S cross by delta p. So delta x can go all the way up to 0 and delta p can go all the way up to infinity. And this is the cause of the divergences in my field theory, and this can be remedied in terms of the renormalization theories. Now, what happens if I introduce gravity into the theory? Then you can imagine QED is compare the strengths of these four fundamental forces. So gravity is the weakest of all of them. Okay, if you normalize it with strong interaction to 1, setting equal to 1, then electromagnetic force 10 to the power minus 3, electroweak 10 to the power minus 13, and gravity 10 to the power minus 39. So that is the scale. So you can practically throw it away. That is what is happening in the conventional field theory. So one possibility is to generalize the uncertainty principle, which I would consider in my next lecture. That would lead me to the, instead of zero dimensional interaction vertices as I have for my particles and fields, which leads to these divergences, I would have vertices that are spread in space-time, and that leads to the string theory. So we postpone that topic for the next talk, and let us come back to the zero-dimensional particles and fields. So what can we do about it now? As an alternative to the string theory, which is one possibility, the other possibility is, can I increase the symmetries in my theories? What is the effect of that? So one beautiful fundamental symmetry of nature is the supersymmetry. Supersymmetry rotates bosons into fermions and fermions into bosons. This is the, so you see, for doing these things, you don't have to think in the first place. Younger people think, can I do it? I am not a theorist. I have not done this. You can start from anywhere, but even awareness is a very good thing. You see, in a place like Germany, where I happened to work for many years, even experimentalists are extremely good at theory, and even theory people have a great feeling for experiments. They all go to the talks of each other, unlike at many places I don't know. So this seminar culture is very, very vibrant in Germany. Every week you have at least 2 talks or 3 talks, okay? Some from internal, somebody from external, and so on. So this interaction is very, very important for this. It's actually, unfortunately, it's not that vibrant in US as it is in Germany. In some countries, the system is there, but you have very negligible audience. I'm impressed that I have 82 audience today, so I'm more enthusiastic while talking to you. This is the so now what could be the other way? The other way could be, could I try making my theory more rich by introducing more symmetry into the theory? Of course, yes, let me try. So what I do, I would like to make my standard model a supersymmetric standard model. I would like to introduce supersymmetry into my theory. So if I do that, I will end up having a supersymmetric standard model. What would happen? The number of particle contents would now be doubled, because there would be a fermion corresponding to every boson and a boson corresponding to every fermion. So the particle content would simply be doubled in the standard model. But now let me first give you, why am I doing it? Is there any advantage of doing this? Yes. Let me, just like the self energy of an electron, let me consider the self energy of a Higgs boson. So what happens when a Higgs boson travels? It can emit a W boson and it can reabsorb it, W boson. This is the self energy diagram of a Higgs boson. If you calculate it, this will be quadratically divergent. Now, if I would like to do it in this supersymmetric standard model, where the number of particle content has got doubled. So I would have supersymmetric particle for each particle of a standard model. So now when a Higgs is traveling, it can split into a pair of Higgsino and a Bino. The supersymmetric particles corresponding to W boson and Bino and Higgsino. Okay, so Higgs and W boson, Higgsino and Bino, and it can recombine into the Higgs boson. Now you make again this calculation. These are simple calculations to be done in quantum field theory too. Now this diagram is also quadratically divergent. The first one was also quadratically divergent. This is also quadratically. But the two have opposite signatures. So they cancel each other exactly. This is a very encouraging result, you see. That if I introduce supersymmetry into my theory, simple supersymmetry with capital N equal to 1, where the transformation parameter is only 1. If I can have 2 supersymmetries, 4 supersymmetries, and so on. You see? Well, there are limits how you can have. So in standard, for a supersymmetric standard model, the upper limit on the supersymmetries is N equal to 4. You can have up to 4. I can tell you how to find it. So here my photon is the particle with the highest helicity plus 1. If I operate 4 supercharges 1 by 1 on this, each one annihilates it once to reduce its helicity by 1/2. So I would get a particle with helicity plus 1/2, then with 0, then with minus 1/2, then with minus 1. So the spectrum becomes complete. Photon with helicity plus 1 and minus 1. And then the fermions with helicity plus half and with minus half. And you can calculate their numbers and the spin 0 particle in between, the Higgs. So this is 4C0, 4C1, 4C2, 4C3. So it will be 1, 4, 6, 1, 6, 4, 1. This is the particle content of a supersymmetric standard model with N equal to 4 supersymmetries. And so when you go to N equal to 4 supersymmetries, the number of particle content has increased. Okay, now you have 6 Higgs scalars. Okay, so and 4 plus 4, 8 fermions of the quark or electron type. Okay, so you will have now too many Feynman diagrams. So for calculating one particular process, you will have to consider many of them. So these days people don't do it by hand. In my PhD days, I had to work them out on paper with my pen. Okay, and again going back to my supervisor for getting checked the different factors of I and Y and so on in between. So you see, this is what I am telling to you. So supersymmetric standard model has got lots of advantages, but still now I come back to symmetries. I told you the local symmetry. So can there be other symmetry? Yes, the global symmetry. In fact, a supersymmetric field theory always has a rigid supersymmetry or a global supersymmetry. So we have the transformation parameter is a spinor, but is a constant spinor. That is the point. So my standard model had gauge symmetry, but my supersymmetric standard model does not have a gauge symmetry. Okay, so I would not have measurable supercharge, the conserved charge for the theory, and then there would be no gravity into the theory. So I would like to now include gravity into the theory. Then what I have to do? How do you construct a gauge theory with local symmetry out of a theory with non-local symmetry or the rigid symmetry? So you take, for example, the massless fermion or the massless complex, and you replace the derivative d mu by a covariant derivative, capital D mu, which involves in its definition little d mu plus minus iota times the electronic charge times a mu. This a mu is the vector gauge field. So you introduce, through the covariant derivative, you introduce a gauge field into the theory. when you introduce gauge field into the theory, this gauge field may not be dynamical by itself. So you introduce a kinetic energy term, which is given by the Maxwell term, minus 1 by 4 F mu nu F mu nu. So the kinetic energy. So then the photon is then dynamical. And this is what you have in your supersymmetric standard model, but then it does not have gravity. So I would like to have gravity into it. What do I do? Then I have to convert this global symmetry into the local symmetry. This is the procedure, standard procedure called as Neother's procedure. So in Neother's procedure, even for ordinary field theory, I replace derivative d mu by covariant derivative d mu, and I introduce the gauge field into the theory, add its kinetic energy. Now, what I have to do, what am I supposed to do for constructing a gauge theory of gravity? A theory of that would be, that is the name I would give it to, supergravity theory. So what is it about? From standard model, I went to supersymmetric standard model. Now I want to go to local gauge symmetry. Local symmetry, so I have to replace that d mu by a covariant derivative. One, in the case of a supersymmetric theory, it will have to be a supercovariant derivative. And the gauge field now is no longer a mu, it's no longer the vector photon. But what you find, this is a spin 3/2 particle, which is a fermion with spin 3/2. This is called as a gravitino. So, and the particle with highest helicity is graviton with helicity plus 2. Helicity is p dot j by p0. Okay, it's given by the representation theory. You can understand it in terms of the, in my other talks. Let me remind my participants and my audience that you can look for my name, Daya Shankar Kulshreshtha, in Google, and you will hit upon my YouTube channel, where I have more than 350 video lectures of mine, including on supersymmetry and many of these things. So please do look for them if you want to revise your things or learn the things. So that is one thing. So now in my standard model, I went to supersymmetric standard model. Then I introduce gauge symmetry into the theory, and this I claim would be a gauge symmetry, a theory having gravity and local symmetry, and that would be supergravity theory, because I have introduced gravity into, and I have to go from flat space-time manifold to a curved space-time manifold. So my metric tensor G mu nu is no longer plus 1 minus 1 minus 1 etc., but in a state it's G mu nu, a function of x mu. So my metric tensor itself becomes a field. In fact, it is the gravitational field. G mu nu of x mu is the gravitational field. And then the theory is invariant under general coordinate transformations, which vary from point to point in the space-time manifold. So this is a very, very beautiful concept and construction. And I wish that we would be lucky that if some of the experimentalists, they get inspired from such work, including my present talk, that I am trying to see. Photon we already knew, the gauge field of QED theory. Now we are talking about the gauge field of the supersymmetric field theory, and this is no longer a mu, but it is actually, it's a spinor vector or a vector spinor, which is a spin 3/2 field. You never came across this prior to supergravity theory. So when you talk about supergravity theory, you introduce in your theory a supercovariant derivative. Through the supercovariant derivative, you introduce a gauge field into the theory, which is a vector spinor or a spinor vector. It carries both the indices. And this is actually going to be gravitino. So you can again have gravity theory, supergravity theory with different number of supersymmetries, like n equal to 1, 2, 4, and 8. Here, the maximal number of supersymmetries would be 8, n equal to 8. Why? Because if I start with my graviton with a helicity plus 2, in a n equal to 8 supersymmetry, I will have 8 supercharges. I can operate on this gluon state with helicity plus 2 8 times with successively with my uh, different supercharges. So it will be 3 half, then 1 half, the spin or the helicity 0, then minus 1 half, minus 1, minus 3 half, and minus 2. So n equal to 8 is a complete theory where you have particles and you can calculate the number of these different particles by 8c0, 8c1, 8c2, 8c3, 8c4, 8c5, 6, 7, 8. So this, this is a simple calculation of these commutations. Okay, so it would be 1, 8, 28, 56, 70, then again 56, then 28, then 8, then 1. So this is the total particle content. If you have n equal to 1 only, oh, life is very simple. You have only one supercharge, you annihilate your gluon state once with this, and you arrive at a particle with a spin 3 half, reduced by 1 half from that of the graviton. So I suppose I take just 10 minutes more to conclude my things. And so in n equal to 1 supergravity theory, I have one graviton and one gravitino. If I have n equal to 2 supergravity theory, what do I have? I have two supercharges. I can annihilate my graviton state twice with two supercharges, once with one, once with another, and once with three of them together. So I have one gluon, two gravitinos, and one photon. So this is actually the dream theory of Mr. Albert Einstein, where he wanted to unify gravity theory with the electromagnetic interaction, and this you can achieve already at n equal to 2 supergravity theory. So I am very sure during the days of Mr. Einstein, all these concepts were not yet developed. He would have been extremely happy to know all these things, and I am sure a giant brain, he would have done much more, not just simply talking about it like me. So you see, this is the power of supersymmetry and the local symmetry, local gauge symmetry, along with coupled with supersymmetry, we end up with supergravity theory. We can go to n equal to 1, 2, 4, and 8. And then, keeping track of time, I would say that n equal to 8 supergravity theory to me seems to be a kind of a complete theory. Why am I saying that? Let me give you a practical example. Let me consider photon going to a photon. Photon scattering going to a photon. Make the calculations of this process using n equal to 1 supergravity theory, and make the calculations also. You have end up with many Feynman diagrams. People have done it. Okay, so it's not hypothetical. What I am talking to is some concrete things. N equal to 2 supergravity theory, where you have two gravitinos. In n equal to 1, you have only one gravitino. Here you have two gravitinos. So then, if you sum all the Feynman diagrams, the result is a divergent result for n equal to 1 supergravity theory. But when you do the same exercise for n equal to 2 supergravity theory with one photon and two gravitinos and one photon, the number of Feynman diagrams becomes still larger. You sum them up, now you find a very beautiful thing. For n equal to 1 supergravity, the net result is some finite number into some infinite contribution. For n equal to 2, 0 into the same number that you had for n equal to 1. So n equal to 2 supergravity theory gives you convergent results for photon going to photon. You see, now you would now I hope it would appeal to you that what I am talking is somehow sensible. It's a sensible theory. Now imagine when I go to n equal to 8 supergravity theory, then what would happen? Now I would have the number of particles would be nc0, 8c0, 8c1, plus 8c1 plus 8c2 plus 8c3. So sum 1 plus 28, 8 gravitinos of 8 different gravitinos. You see, we have not yet been able to discover one gravitino. So just think of the framework. 8 gravitinos, then 28 vector particles like photon with spin plus 1 and 28 with spin minus 1. Okay, so just think of all these things. Okay, then fermions, 56 fermions with spin plus 1 half, 56 fermions or electron type particles with spin minus 1 half. And there was a lot of hue and cry in the media when we discovered one unique Higgs scalar for the standard model. Now there would be 70 Higgs scalar bosons in my n equal to 8 supergravity theory. And as I showed to you, the divergences start cancelling already when you increase the symmetries of your theory. So this is, I think, is a very, very well-defined route to construct. You see, the aim of supergravity theory as well as that of superstring theory is the same, to construct a theory of quantum gravity. So here we stay with zero-dimensional particles and fields in supergravity theory. In string theory, we go to extended objects called strings. We postpone that further discussion on that for the next talk. Now, I come back to supergravity theory and I start concluding my things on that. You see, what happens in supergravity theory, we do not need the process of renormalization at all. Why? Supergravity theory is convergent order by order. It's finite order by order. And therefore, supergravity theory has finite predictive power. This is the beauty of this theory. And in 76, all this, what is the fundamental physics prize went to these three guys, what were the name? Friedman, Sergio Ferrara, and Peter van Neuwenhuizen. A difficult name, but the Dutch name. So these three, for developing, and Dasser and Jumino independently developed this supergravity theory, including their couplings. You see, you have so many particles, we don't yet know the couplings are not yet measured even for our standard model, simplest model. So think of supersymmetric standard model, think of supersymmetric supergravity models where the contents, number of particle content is so large. Then how do these particles after all talk to each other? We are talking to each other via this availability of a internet and this link from your Google Meet. So, or you could have Zoom. So there is some media to talk about. I am speaking some language which is understandable to you, you see. So we are able to communicate with each other. So these particles talk to each other via the exchange of these different gauge bosons, vector gauge bosons. In supergravity, they are not bosons, they are fermions. So gravitino is a fermion. And not only spin 1 half, but spin 3 half fermion, which we have not known. Now, let me mention you, not many minutes are left. One very close friend of mine works at the University of Groningen. He's a very famous general relativist, Anupam Majumdar. And he has a lot of collaboration also with leading experimentalists. So he is performing a tabletop experiment for the experimental detection of a graviton. You see, if we always depend on these conventional experiments like CERN and Fermilab and so on, I don't know how much success, how fast we get the success. But so we have to encourage the smart, intelligent experimentalists, you see. They can come up with ideas. So this Anupam Majumdar, this team led by him and with many others, they are doing a tabletop experiment to detect a graviton. I would suggest and recommend that people should think in terms of making tabletop experiments for detecting a object called gravitino. What are you going to get by detecting gravitino? You at the At the same time, you get too many things. You verify supersymmetry, you verify supergravity theory, you verify quantum gravity, all in one go if you can discover a gravitino. So if you depend on CERN, it will take, I don't know, a lifetime. You have to think of alternative smart guys, smart experimentalists, and you have to think of beautiful ideas, and you have to make things work. So, but I would say that supergravity theory is a theory which is very rich in symmetries, which has predictive power. It's finite order by order. So what happens? Why is it finite order by order? You see, I have too many things to tell, but time is limited. So here the divergences in supergravity theory, they cancel at the S matrix level. They cancel at the S matrix level, and that is the reason you don't need renormalization of the theory. So in supergravity theory, you don't need the renormalization at all, which we heavily depended on renormalization in our conventional field theory, conventional quantum field theory, and standard model physics. But now, if you aim at doing super model, I don't know what you like to call it, these particles, 256 particles with all these helicities plus 2 minus 2 in between all these particles, they can be considered, a graviton can be considered as a supergraviton with all these other particles as the different polarization states of this particle, you see. So it's a very, very beautiful idea, very rich idea, and here you don't need to, because you are staying still with the zero dimensional particles and fields. Okay, in string theory we would have different problems, I would talk about it later, but in supergravity theory you are staying with zero dimensional particles and fields. So that is the advantage of this supergravity theory, and aim is of course the same. Whatever aim we had for the other theory, we have the same for this theory. And I would personally, but supergravity theory in fact turns out to be a low energy limit of the super string theory. So as I said, the Planckian scales and our standard model is able to make contacts with observational physics, okay, with the laboratory. That is our aim. We have to, whatever predictions, unless you can make contact with experimental observations, it doesn't make any sense. So here the energy scales as compared to the Planckian energies are very, very small. So in between there is a huge gap, huge sector, and this supergravity bridges this gap between the standard model or supersymmetric standard model all the way up to supergravity or n equal to 8 supergravity theory. So I have personally a very great feeling for pursuing this path, and I would encourage my younger generation to, even if you don't want to do supersymmetry or supergravity theory, or no problem, but one should keep an open mind to learn. These are some very, very simple fundamental ideas, some very, very simple fundamental concepts which make use of very simple ideas in physics. So I would personally encourage everybody to have high hopes on this, and possibly at least try to learn, try to become familiar. You don't have to become friends with everybody, but there is no harm in just exchanging hello and trying to know the person a little bit. You people are too nice and gentle. You would not like to tell me that I should quit, but my watch tells me that I have been speaking for about 1 hour and 10 minutes. So I can suitably conclude at this point. Then we will make a short gap of, let us say, 5 to 10 minutes, less than 10 minutes, because I waste a lot of time in many other things. I wasted several minutes before beginning this talk of mine. So if you like, I can conclude here. If you like, you can ask me some questions now, or maybe at the end of second talk, or now, as you please. I leave the I make space for the chairperson.
Any questions?
I have a quick question regarding the detection of gravity law, which you mentioned. Uh, your friend is using a tabletop setup, right?
Yes.
So I'm wondering what is the energy involved, because CERN and other big colliders are required to study smaller particles like it. So how can we imagine something like what is the
I think
energy level one can be?
very good. I think it's a very very fundamental question that you have raised. I would tell you a few nice things. In the first place, I would give you the references that you please have a look at the papers by Stan Brodsky and company. Stan Brodsky is a good friend of mine, works at SLAC, Stanford, and he has suggested, for example, ways to detect supersymmetry in hadron physics. You can think now, relatively much smaller scales. This light cone meeting is already going on in Rio, and I could not make it to. I could not travel to Rio. They first wanted to accommodate through online talks, but then they said, okay, there are too many people around. So finally, they are doing it offline. So tonight I will have a meeting with them online for the annual meeting. But I'm sorry I could not make it personally because I was scheduled to give a lecture there. So this friend of mine, Stan Brodsky, you look at some of his papers, very famous papers. They talk about signatures of supersymmetry in hadron physics. So, I mean, this is just an indication that you see, you can look for things. You have to think of many alternative. I'm not sufficiently smart actually, Nirmalji. I'm not sufficiently smart to think. But I would suggest that you also please look at the work of Anupam Majumdar from the University of Groningen. What is he doing? Okay, and he's a very friendly person.
Sure, sir.
He's a very friendly person. I have met him several times, heard his talk several times. It's only 2 hours distance from Oldenburg in northern Germany, which I happen to visit, and he comes very often there also. So please look into the work of Anupam Majumdar and company. What are his plans? What he thinks? Wow, I may not be smart enough to understand all that, but if you have this curiosity, please do look into at least these two sources I have given: Stan Brodsky's papers on supersymmetric hadron physics. On the one hand, even finding supersymmetry would be something, you see, and then looking at the work like that of Mr. Anupam Majumdar, how to reconcile with many other things. But keep your this curiosity alive, dear friend. Don't give up after my talk. Please don't give up these ideas. Okay, and
Thank you, sir.
encourage
Thank
all
you.
others also to pursue it.
Right. Right.
Any other questions from the audience?
Hello, sir. Yeah, it's nice talk. Sir, actually, I consider about the last year. There's a lot of news about the LSC didn't see any particle belong to the supersymmetry. So you can make a comment on that part.
Yes,
because
sure,
there's a lot of
sure,
news
sure,
there.
sure. You see,
Thank you.
in LHC there are some limitations. You see, if you make proton collide, at how much energies you make them collide? Okay, so present accelerators have the limit 10 to the power 16 GeV or something. You can look into it. I'm
Yeah, 14 GeV central mass. Yeah,
Yes,
around 14 GeV.
because
TeV, sorry, 14 TeV.
yes, because I might give you wrong numbers. So with that you can probe physics up to the level 10 to the power, let us say, minus 16 centimeters. Okay.
Yes.
And
Yes.
for going to 10 to the power further, you see, so that is one. I agree but this is not the end of the day.
True.
This is not the end of the day. You see, 100 years ago, we did not have aeroplanes. We only
True.
have some paper aeroplanes, okay? As a toy model, हम और आप बनाकर फेंकते हैं और उनसे खेलते हैं बचपन में. But now you have big cargo planes. The first metro coach came from Germany in an aeroplane. It landed in Delhi. I was so fascinated, you see. When I used to travel in Paris in the year 1980, in the underground metro, going to several floors underneath the surface of the earth, I used to worry, oh, I have crossed Seine River again and again from below. When will it come to India? And now we have metros almost running everywhere now, and it's increasing, expanding. So you see, now we have landed 3 times. I mean, we have made it to moon 3 times, let me say. In my third talk on Friday, I would talk about all those things. So some people, they ask, oh, some people want to make jokes on this. This is nonsense. You see, we made one trip, then second trip, then third trip, we have put our rover there. We have put our lander there. This is a great success. How far we can go in 100 years, you see. You and me don't have to be there again, because then I don't have time. I had some comments. If I have time in that second talk, I will tell you a few things out of Bhagavad Gita. It tells us very, very rich concepts. So this is not the end of the story. It's only the beginning. And you see, one day might arrive. Modi ji said, Chanda Mama, sirf ek tour ke. You see, so you can possibly travel too often there. You don't need to Mr. Elon Musk to help us do that. India also has brain power. We have very talented people sitting just here in my audience. I am very sure. We don't have time, otherwise I would have loved to talk to each one of them. They are very, very bright people, very curious minded, enthusiastic, bright people. I have hopes on all of you. In the second topic, if I find time, we are going to talk for 2 more times. I would leave some responsibilities on you, give some more motivations.
Thank you, sir.
थैंक यू सर. तो हम 5 to 10 minutes के बाद दोबारा assemble हो जाएंगे.
बिल्कुल.
3:45.
Yeah. We try to assemble back in 10 minutes, and then.
Yes,
Okay.
sir.
Okay.
Continue with the next lecture.
Okay.
Thank you.
Okay. Fine. Thank you.